Hello, thank you very much for giving me the opportunity to present an overview of our work in the context of this workshop. My name is Kaspar Althoefer and I'm the head of the Center for Advanced Robotics at Queen Mary. And today I would like to talk about tactile sensors for robot hands towards intelligent manipulation of soft robots. Recently there has been a recognition of how to really look at robots and not to just look at them in isolation, but to see how they interact with the environment. Different solutions have been found, and really very clear is that the robot needs to be seen as something operating in its environment. And so one approach is to equip standard rigid component robots with sensors that can measure the interaction and then have a control architecture that would react accordingly to achieve a compliant interaction. Other approaches look at integrating passive elements that make the robot more compliant. So one approach here is the series elastic actuator that has been successfully employed in the Baxter robot, which I call here soft, because even though it is made of these rigid components, but still it has the ability to interact with the environment in a compliant way because of the elasticity that is built into the joints, and for that reason it is now approved to be used in the vicinity of workers in a factory environment, for example. Other approaches also include the inclusion of passive elements, and so here is the soft hand by Tonio Bicchi, and as you can see, it is capable to compliantly adjust to this environment that it is involved with. So others have looked into going a step further, and here is an example where we take inspiration from biology to now create devices that are completely soft. So silicon-based, pneumatically actuated robots that take inspiration from the octopus as an example here. And as you can see, it can squeeze through very narrow openings and still apply forces to the environment. So taking that further, we have created robotic devices that take this idea on board and can be used to interact with the environment. So for example, this prosthetic robot hand on the left hand side, but also the gripper that can be used in a manufacturing environment. And here we are really moving to the complete other side of the spectrum and have something that is very soft, very compliant, but also very adaptable to that environment we are involved with. And yeah, important point here is why I'm making these points, that now if we look at sensing, of integrating sensors with these robotic hands, we have to of course look at the material properties of these robotic devices and find sensors that can do the job as required. But also it is important to understand how these robotic devices are interacting with the environment and how and what kind of sensing capabilities are now needed to measure what's happening at the point of contact, at the point of interaction. So I would like to give an overview of manipulation tasks. So here we can see Jeff Bezos to using a very advanced robotic hand, the shadow robot hand, and is actually now capable to do quite skillful manipulation. However, I have to say this is teleoperated, and still it looks very clumsy, even though he's doing quite a good job there. Another example, looking at what is being done at Cornell University and really making the point here, I mean, looking at what our hands can do, being able to move objects around in a very skillful way in hand manipulation. And now here we see the solutions by Rob Shepard at Cornell University now, and very much a focus on creating a compliant device, but also to integrate sensing capabilities to understand the interaction with the environment. And so what they have achieved is really a good measurement of the forces involved, good tactile information coming back, capable of classifying between different objects. But if we compare that to the skillfulness of a human moving things around, still more needs to be done. So other work in this direction, looking at in-hand manipulation, has been done at the Technical University of Berlin. So here I want to mention Oliver Brock with his approach to do in-hand manipulation, and we can see here the robot hand is now programmed to move the cube inside the hand, so already moving really in the right direction. And here's a comparison to other robotic hands, and one of the findings actually is that with his robotic hand, the one that is being developed at the Technical University of Berlin, they are capable to do this in-hand manipulation without or with very little sensing capabilities integrated. And that's where they really distinguish themselves from robot hands made from rigid components. Moving forward, I would like to mention work that has been carried out at Queen Mary, my colleague Lorenzo Iamone, and he is also very interested in creating sensors that can be integrated with robotic hands or robotic fingers and can help with manipulation. And so if we look here at a later part of this video, we can see here a robot hand, and that is equipped with magnetic 3D force sensors and has the capability now to give relevant or acquire relevant information about the interaction with objects that are being handled. So I move forward a bit here, and the video is not running, and now it's coming. Good. So here we can see the robot hand now in action using the magnetic sensors, and they provide now 3D force information in this particular case. And as you can see, the interaction forces are being measured, and the control mechanism then reacts to that and applies the right force, and in this way slip can be compensated for or can be avoided. Other examples include work at RSCL, KaiTech, and again looking into trying to find solutions operating robotic hands and manipulating objects in that hand. And again, the sensing aspect is important here in this context. Other work, very recent work, has been carried out at Harvard University, and Robert Wood is the lead there. And so they also have looked now into the problem of in-hand manipulation, have gone also the soft route, and as you can see, quite successfully these robotic devices can carry out in particular these rotary tasks that are needed often in in-hand manipulation. They can grasp objects and then move them, gate the fingers over the object, and move the object in this way from one position to another. Now, various sensors have been developed in the past for robotic hands, and I think it is very important to look at first into the requirements. So what kind of robotic hand are we using? Is it a compliant one? Is it a soft one? Or is it one that has rigid components and possibly is operated by stiff joints, stiff actuators in those joints? And that needs to come into the consideration when deciding on the right sensors for the particular task to be carried out. And so here is an overview of a number of sensors that have been developed in recent times, and there is more and more also recognition of using compliant hands, compliant robotic grippers to achieve this task of manipulation in an easier way. So moving away a bit from the idea of using those rigid component robots with their stiff joints. And obviously, if we look into that, then we also recognize that the sensors that we need for these more novel, soft type of robots need to be adapted in the right way so that they can be integrated with those robotic hands. Or in other words, I mean, a rigid sensor cannot be integrated with a soft robotic hand. Now, we have worked in particular on optical approaches for tactile and force sensing, and I've presented that already last year. Our main approach here is to observe the deformation of a tactile element, and the observation we do through light. So we have an optical approach, and here we are looking at how this element, this tactile, this mechanical element is deformed and or displaced, and then we use an optical approach measuring the light intensity, change of light intensity, to then relate what we measure, the light, to the forces that are being applied. And we have applied this to a number of tools. So for example, a palpation tool for minimally invasive surgery. And so if forces are now applied, that changes the light intensity in that tool, in that instrument, and that relates to the forces applied. And so we can see that here in action. We are rolling the tactile tip, the sensitive tip, over tissue, and the forces are being relayed back. And that allows us now to distinguish different forces, and in this way distinguish between stiffer areas that could contain tumor and the healthy tissue that is softer on the other hand. Taking this a step further, we have developed an approach whereby we again look at the light intensity variation. However, now instead of using standard optoelectronics with an individual light sensitive element, we have now moved forward to a new approach whereby we take in the light intensity information and send it to a camera, as we can see here in this diagram. And in this way, we can create now very cheap devices, tactile sensing systems. We can have easily highly distributed sensing systems, and so we can now in one go take information from multiple points. So as you can see here, we have a 3x3 tactile sensor integrated into a robotic fingertip. And then through an image processing approach, we can effectively compute the forces that are applied at the individual points of our or the tactiles of our sensing system. We have also taken that idea to measure forces along multiple axes, and so here in this case we have created a system, a sensor system that can be integrated in a catheter 3 millimeter diameter, and again we're sending out light information to the tip, and that tip is mechanically sensitive, deforms when forces are being applied in the three main directions, and that we feed back then into a camera. And we can see here the 3 points that are fed back from the camera via the optical fibers, and we can now very easily identify the forces in the 3 directions. And yeah, so that allows us now to create very low-cost sensing systems, but they are also very easily expandable because we are using here only 3 spots on the camera. Thousands of spots could be imagined, so we could have highly distributed tactile sensors created in this way. I want to now move a step further. We have taken that idea of the camera-based sensor to another level, if you want, and we are looking here at a system that is capable of measuring tactile information and force information in one go. So here just a few examples. So that is work by Toyota Research. I think a fantastic implementation of that idea. So we have this very soft, tactile area, and behind that is a camera system that watches a patterned surface, as we can see here, and then by interpreting the camera images, by using optical flow techniques, for example, we can calculate what is the tactile information and what is the force information that is being applied. And as you can see, the system is even capable of understanding slip and can then react very easily to it. Another system in this context is Tactile from the University of Bristol, and we see here a very similar approach integrated in this fingertip of a robotic device, for example, and we have a dome-like structure that is soft and can deform when brought in contact with the environment, and this deformation then leads to the distortion of the points that are painted on that soft surface, and we can from that then receive tactile information, but that can be then also through some processing. AI techniques are being used there, be used to measure forces. Obviously, in this context, I need to also mention gel sight, which has been around now for many years. I think a fantastic start was done there by the researchers. The same idea is being applied here, and so we can see now the geometry. So a fingertip is being pressed onto this soft material, and at the same time these pixels drawn on there are deformed, and we can use this to measure the local force information. This has been also further pushed, and so systems have been developed in the context of the gel sight development to integrate those with robotic grippers, and we can see during grasping we get a lot of tactile information from the interaction with the object, as we can see here. And so we were so excited by the gel sight sensor that we have recreated it in our labs at Queen Mary, and we can show it here. So we have now this very tactile area on top, and so you can now interact with the environment, and that can be seen. So the geometry of the object is visible, but at the same time we can now, through understanding the movement of these drawn on pixels, what forces are being applied and which direction they go. Now we have taken that a step further and have developed F-Touch, and the main point is, and I'll go through the stages here of the work that we have done. The main point here was really to combine now the tactile information with some force information. While GelSight and other systems of that nature just use the deformation of the soft material to compute the tactile information and the force information, we have taken it a step further and have integrated in the overall structure force sensors. And these force sensors are effectively also just deformable elements, but these are observed by the camera. So again, it's just a single camera that is being used to observe now the tactile information and the force information in one go. And so we went through a number of stages there, and here you can see our success in being able to measure tactile information. You see the deformation of the the membrane in the left-hand side. But most importantly, we have now integrated the tactile information with those force sensors. As you can see here, we are applying now, we are interacting with certain objects like cylindrical ones or rectangular ones, and we can see that, so the geometry comes, the tactile information comes, but at the same time we can now compute the force information by observing how now these these force elements that we have integrated move in front of the camera. And so that is another view of one of our systems being developed. I just move forward now and show here an overview of the whole system, and I think that makes it more clear. So two components that are important. One is the elastomeric component, so our silicon block, if you want, that can deform and can see the geometry of an object that is in contact with that. But in addition, we have now multiple springs, or 6 springs, and by observing now the movement of the springs with the camera, through the camera, we can measure 6 degrees of freedom information, force information. And we can see that here in action. I go quickly through that. So we apply now forces in different directions, and the sensor can let us know what the forces are, the amount of forces, and in which direction they are going. And I move forward. So we can also now introduce an object there, and so we can now observe the forces. But if you look at the left-hand side, we can see also the shape of the object that is brought in contact with our sensor. Good. So I just wanted to make one more point, especially in the context of manipulating soft objects. And even though I made this point last time, I would like to highlight that again. The importance, in my opinion, the importance of integrating proximity sensing with tactile and force sensing. So here we are looking at a fingertip sensor integrated with a force sensor, 3-axis force sensor. And on top of it, we have integrated proximity sensors. And that allows us now not only to measure forces, but also to measure the distance to the objects nearby. And we are again using an optical approach to achieve that, and integrated that into a device. And now the important point, if we think about soft objects, we have now the capability to measure the force information. So we know what force is resisting now when we interact with this soft object, here this foam, and at the same time, through the proximity sensor, we can measure the deformation. Now, bringing that both together allows us to compute the stiffness of the object that we are interacting with. I just want to conclude with mentioning with great thanks the various funding sources that have supported our work. And obviously many collaborators have been on board to help achieving that. Yeah, that's not just work by myself. I cannot these days conclude a presentation without highlighting that we will be organizing ICRA 2023, May to June, 29th of May to 2nd of June 2023, ICRA in London. And that brings me to the end of my presentation. Thank you very much.